Okay, welcome to the afternoon session. It's Igor. Go ahead.
Thanks, Gabor. I'm very happy to speak about this thing about global freezing for two reasons. First, because it's winter, so I thought it could be appropriate. And second, because everything began 2 years ago at a RandNET conference in Eindhoven. And let me tell you about the motivation concerning what I am going to speak about. It was an open problem suggested by Arthur Blanc-Renaudy at the open problem session from 2 years ago conference at Eindhoven. And the question, wait for it, is the following. So first I will give you an informal description, and in the next slide a more formal description. So imagine a group of people, everyone interacting with everyone, and consider an epidemic starting in this group with one infected person, and in this group people can be healthy, susceptible, infected, or recovered. And people who are ill recover at a certain rate, and when you are recovered, you cannot get infected again, and you can get infected only once. So it's a classical SIR epidemic. And you draw an edge between two people if one infects the other. Since you can get infected only once, you get a tree. And what does the final tree, the so-called infection tree or the epidemic tree, look like? You have 1 hour. So let me be maybe a bit more precise concerning the model. You have n people, one person initially infected, n minus 1 susceptible, n people in total. So you have the initial conditions. Recovery of infected people happens at rate 1. It means that as soon as you get infected, you have a clock, exponential clock of parameter 1 which starts, and as soon as it rings, you get recovered. And infections between any infected people and any healthy people happens at a certain rate, lambda n. Okay, so it means that at every edge between an infected person and a healthy person, you have an exponential clock of parameter lambda n, and as soon as the first clock rings, it can be a recovery clock, it can be an infection clock, well, something happens, and then you continue. Okay. So if you want, this means that conditionally given the system at time k, if the infection has not died out yet, the probability of having an infection, it's the total rate of infection. Why? Well, you have ik infected people, sk healthy people, so this is the total number of edges between infected healthy, and lambda n is the rate, individual rate for every one of this thing to happen. Okay, so you get these probabilities. So you get a nice Markov chain, which has quite well been studied. There are fluid limits, stuff like that, in the large n limit. Okay, so this is just a Markov chain. Great. But now you add, you do a graph, you draw an edge between two individuals when one infects the other. And the question is, what does the final tree look like? Is the model clear? If at any point something is unclear, please do ask. So several possibilities. Result 1. Oops. It's going to come back after an exponential clock. Yes, great. Result 1. Does it look like this? Does it look like this? Does it look like this? Or does it look like this? So you have to vote. You have to go on the website, wooclap.com. You enter the code RandNET, and then you vote. So I'll just put it here. It's going to come back. right now.
Is the voting anonymous?
I collect only your credit cards. If at some point it asks for a credit card number, it's perfectly normal. Yeah, it's anonymous. I don't know what this website does with your IPs, but I don't collect them. So we can see that 3 people have voted. It's here. I'll leave you a bit more time to vote. How many? So we should have 27 votes. Give you a few more seconds, and then we will reveal the results. 3, 2, 1. Okay, so this is the results. So let's see. What is the correct answer? Well, the 4 results are the correct answers.
It's like more than one.
Yeah. Yeah, you can vote more than one for more than one possibility. Yeah, actually, depending on this lambda n, this rate, if you take lambda n very, very small, it means that infection don't happen a lot. So recovery will happen faster, so you will get a very small tree. Okay, if lambda n is equal to 0, no, wait, what does that? Yes, when lambda n is equal to 0, this means that you have no infections. So if you have no infection, the first people gets recovered and you have only one vertex. So this is actually the case where lambda n is very small. And here you go through different regimes when lambda n increases. And so the goal to understand this picture, first, observe that this is incorrect. When lambda n is equal to 0, as I just said, you have no infection, so you just get a tree with one vertex. But when lambda n in the other limit goes to infinity, you take lambda n equal to infinity, so no recovery, essentially. When you have only infections, what happens? You get a uniform attachment tree, a random recursive tree. Because when somebody gets infected, well, who is it infected by? Well, uniform choice among the infected people. Okay, because this is a well-known property that you know among exponential random variables. If you have KIID exponential random variables of parameter 1, you look at the smallest one, well, it is uniform among the K. So when lambda n is equal to infinity, you get a random recursive tree. So let me remind you what this model is. It's a sequence of recursive trees starting from one vertex. At each step, you add a new vertex and you attach it to an existing vertex, which is chosen uniformly at random. Okay, this appeared in Luc's talk last week. And the question we are asking ourselves essentially in this talk will be what happens in the large n limit. What does our objects look like when n is large? So this is an informal question. Maybe a bit a more formal question is what are the order of magnitude of the graph distances in Tn? You can think about the largest graph distance you can find, the diameter. You can think of the height of the tree, which is the largest distance from the root to any vertex. You can think about the 1 point, function. You take a uniform vertex and you look at its distance to the root. Or you take 2 uniform vertices and you look at their distance between them. So here is what a random recursive tree looks like when you increase the number of vertices. So it's quite bushy. And concerning the distances, the following result has been obtained a few days ago by Luc. Happy birthday, by the way.
It's not today.
Nearly, from what I was told. Dn is the graph distance on the random recursive tree. The height is the maximal vertex from the root. We know that the height of the tree is of order log n. Divided by log n, we converge in the probability to E. And if we take two uniform vertices, the distance between two of them is of order log n, and scale they converge to 2. And the distance from the root to a uniform vertex is of order log n. So what does this indicate? This indicates that if you take two uniform vertices, let's say here and here, what is the geodesic between them? What does it look like? It will essentially go through to the root. This gives log n. It gives up log n. So log n plus log n, 2 log n. So typical vertices are all at the same height log n. But you have atypical tentacles, branches, of height e log n. And you don't see them if you take 1 or 2 or 3 points uniformly at random. Okay? This is what this indicates on the geometry. Now I will introduce a variation of this model where we introduce freezing. This corresponds to the recovery in the infection tree model. So what is this model of recursive trees with freezing? You start with one vertex, which is active. Now we will have active vertices and frozen vertices. And you add, you get from step n to step n minus 1 by doing either one thing or the other. First, you can freeze an active vertex chosen uniformly at random. Or you can add a new active vertex and you attach it to an existing active vertex chosen uniformly at random. Okay, this means that once a vertex is frozen, you cannot attach to it any more vertices. Okay? Its degree will be frozen. Is the model clear? So what does a large random recursive tree with freezing look like? Maybe it looks like this. Maybe it looks like this. Maybe it looks like this. Or maybe it looks like this. So I can give you a hint. They all have 20,000 vertices. So you have to vote. So leave you a few more seconds. So it looks more, how you say, close. And indeed, the result, the correct answer is with 1, 2, 3, and 4. Actually, depending on how you choose either to freeze or to add a vertex, you can get any 4 of these regimes, which will be regime 1, regime 2, regime 3, regime 4. So what happens in the first case? Essentially, in the first case, you have quite a lot of freezing. Essentially, what you do to get result 1 is you add, you freeze, you add, you freeze, you add, you freeze, you add, you freeze, you add, you freeze. so that at every time you have only 1 or 2 active vertices. So your sort of front, how you say, your front of active vertices is very small, and in that way, essentially, you just get something that looks like a line. And in result 4, here you have not a lot of freezing at all, so this looks very much like the random recursive tree. Okay, and the goal will be to identify 4 very different regimes and to study the geometry and get limit theorems on distances, height, typical distances, and so on. Is the model clear for everyone? And of course, we will have to impose conditions on when do you freeze, when do you add, do you do it at random, do you do it deterministically, how do you do that? You have a lot of freedom. Some more motivation. If you are as much addicted to Twitter and Instagram as I am, you know that you can deactivate your account. It means that nobody can follow you anymore. So you freeze sort of your account. Okay, but the main motivation, this is why we introduced the model, it's because of this infection tree model. Okay, because the infection tree can be seen as a random recursive tree with freezing. Okay, indeed, first you do your SIR Markov chain, so you don't care about the geometry, you just care about the evolution of healthy people, infected people, recovered people, so it's just a Markov chain. And once you have this Markov chain, okay, so first step of randomness, second step, when you have an infection, you do an attachment, and when you have a recovery, you do a freezing event. So you have sort of 2 steps of randomness. First, some way to know when do you freeze or when do you add, which is random. Okay, it's driven by a Markov chain, and then you build your random recursive tree with freezing, given this input, which was random. So let me now define more precisely the model. Consider a sequence of +1s and -1s, and you build a sequence of trees starting with 1 active vertex, and then if you have no more active vertices, well, you don't change the tree. If you read a -1, you freeze an active vertex chosen uniformly at random. If you read +1, you add a new active vertex and you attach it to an existing active vertex chosen uniformly at random. So this sequence of +1 or -1, this is sort of the, how you say, the parameter of the model. And the question is, what is the influence of this sequence, this sort of parameter, on the geometry? Okay, you can take the sequence deterministic, you can take it random. Okay, maybe if this sequence satisfies certain properties, you will really look like a line. Maybe if it satisfies some other properties, it will look something else. So essentially what we will do is that we will impose conditions on the sequence X, and we will see how it changes the geometry of the tree. So let me give you a quick example. If you have, for example, this sequence, +1, -1, +1, so -1, you start with 1 vertex, 1 active vertex. You add a new active vertex, you don't have much choice, so you attach it to the existing vertex. Now you read -1, so you have to freeze one of them uniformly at random, let's say this one. Here I write 2 because I freeze it at step 2. Now +1, I have to add it to this vertex, and I put 3 on this edge because it happened at step 3. +1, here I have a choice, okay, let's say this one, and -1, and so on. Okay. Now a key thing to observe is that the number of active vertices at a given step is just 1 plus the sum of the increments, +1 or -1. Okay, because +1 you add an active vertex, -1 you remove an active vertex. So this is the crucial quantity of interest, Sn. Okay, it represents the number of active vertices at time n. Okay. Now a further motivation. So as we have seen, if you take only +1s, no freezing. So we get the model of random recursive trees. Now, I claim that this model also encompasses the classical model of uniform plane trees, which has a completely different geometry, which does not have height log n. Indeed, choose your sequence X a bit as in the infection tree case, at random. How do you choose that at random? You just choose the plus or minus 1 uniformly IID, plus 1 probability half, minus 1 probability half, but you condition on the fact that this walk SK, it's an excursion. Okay? It starts from 1, it goes plus 1, minus 1, and so on and so on, and you condition it on being back at 0 for the first time at time 2n minus 1. Then it turns out that this random recursive tree with freezing is actually a uniform plane tree with n vertices. Here maybe you wonder, yes, but this tree has no, it's not plane. Here I'm speaking about uniform plane trees. You just root your random recursive tree at the first vertex, the first active vertex, and the plane order, you just take a uniform order among all the children. In that way, the random recursive tree with freezing tree, you can view it as a plane tree. Take a uniform plane order. And this is something which is not too difficult to see, but it's a nice result, let's say true for every n, not in the limit. It's a sort of combinatorial identity. So now I can give a rough sketch of our results. So essentially, our regimes we're interested in is when the number of active vertices, as time goes, evolves as the number of vertices of the tree to some power. More precisely, you fix a sequence of plus 1s and minus 1. Recall that Sn is the number of active vertices at time n. And essentially, what we assume, our main assumption, is Sk of order k to the alpha. So alpha equal 1 is typically the case for the random recursive tree, because you take only plus 1s, so Sk is k. In the uniform plane tree case, when you get a uniform excursion, maybe you know that a uniform excursion of length k has height of order square root k. So the uniform plane tree case will be the case alpha equal 1/2. But you can ask more generally, what happens if you just put power alpha here? And we identify essentially a phase transition at alpha equal 1/2. Here, indeed, for alpha equal 0.3, this was the first picture you saw. This is for alpha equals 0.3. So I took here, here I have represented Sk as a function of k. So you see that this, the choice of plus 1s and minus 1s I made, it was done in a way that it looks really like x to the alpha with alpha equals 0.3. The fact that you see here, this means that you do a lot of minus 1 plus 1, minus 1 plus 1 during a long time. And this is the subcritical case. We essentially show that distances are of order n to the power 1 minus alpha. It means that the length of this line will be n to the power 1 minus alpha. And the scaling limit, in a sense that I will explain, is a line. It means that you have some branches going out, but when n is very, very large, the lengths of these lines will be little o of n to the power 1 minus alpha. You have outgrowths, but they vanish in the limit. Now alpha equals 0.5. Here we have non-trivial scaling limits. We will see that distances are of order square root n, and the scaling limit, you have a scaling limit in a sense that I will define, is a random tree, which is a random compact real tree, which in the case of uniform plane trees is the Brownian continuum random tree, as we will see a bit afterwards. Now alpha equals 0.8. Here we are in the so-called supercritical case. Distances are still of order n to some power, always n to the power 1 minus alpha, but here the tree looks like a star in a sense that I will also explain. We don't have scaling limits. It's too bushy. It starts to become too bushy when alpha is greater than 1/2. And final case, alpha equal 1. So here f of x is x over 3. So this essentially is doing plus 1 plus 1 minus 1, plus 1 plus 1 minus 1, plus 1 plus 1 minus 1, and so on. And here we don't have distances of order n to some power. We have distances of order log n, really like the random recursive tree case. It's really like a bush, and it also has no scaling limits. This is a bit imprecise. I will give formal assumptions and formal results afterwards. Yes?
Is the X deterministic here, or do you sample it?
So essentially, here, as soon as you satisfy this informally, you will see this. So if you sample your X at random, and with high probability it satisfies this, then you get something that looks like this, which is random, but looks like this. Yeah. And this is essentially what we do to get results on the infection tree. We show that with high probability, the sequence of +1, -1s you get from a SIR epidemic satisfies with high probability a certain property. And if this property holds, we understand the geometry of the tree.
Yeah, like the most concerning case for me was the first case with you've got the line.
Yes.
Like there's a chance that you can freeze all the vertices, right?
Yes, that's right.
This cannot continue.
Yes, so that's why this is quite informal. The assumption we will make in order to have a tree with n vertices is that the epidemic does not die out. So, yeah, you're right. Because, of course, maybe what happens here, if you go beyond 0, very at the beginning, well, you stop. So, indeed, you need to impose a bit of conditions at what you see near the origin. Yeah, thanks. Other questions? So I was speaking about the notion of scaling limit. What does it mean? The notion of scaling limit is something about convergence of some, morally speaking, discrete objects to some continuous object in a certain sense. So why is that useful? Well, you can go from the discrete world to the continuous world. If your goal is to study X, a limiting object, you can show that Xn satisfies a certain property. If the property passes to the limit, for free you get that the limiting object satisfies this property. And you can go also from the continuous world to the discrete world. If your goal is to study Xn, you can show that X satisfies a certain property, that this passes through the limit. Then in a certain sense, for n large, in a certain sense, Xn should approximately satisfy this property. Okay, this is the intuition. And then you can do both. You can go from the discrete to the continuous and from the continuous to the discrete. Let me explain this here. Imagine that your goal in life is to study Xn. So to study Xn, you can show that Xn converges to X, Yn converges to X. You show that Yn satisfies P, so X satisfies P, so Xn satisfies P, and you are happy. You can say, why do you do that? Why don't you directly show that Xn satisfies P? Why are you making your life hard? Well, the reason is that since these are discrete objects, from a combinatorial point of view, Xn can be much more complicated to study than Yn. So this is essentially something about a perturbative argument. Microscopically, you modify Xn, you get Yn. Doesn't change the large-scale properties, but for combinatorial reasons, this microscopic modification you make makes the thing very simple to study. It's a sort of perturbative argument. Now let me be a bit more precise. When we speak about convergence, in what sense? In the sense of convergence in a certain metric space. When we have points in the metric space, we have a notion of convergence coming from the distance in the metric space. But what about randomness? When the objects are random, what is the notion of convergence? Well, as often for random variables taking values in the same metric space, we use the notion of convergence in distribution. Xn converges in distribution to X if for every continuous bounded function f, real valued, expectation of f of Xn converges to expectation f of X. So intuitively speaking, you can view this as an abstract convergence. And this abstract convergence sort of is materialized by the fact that for every observable f, so you look at your object, you observe it, you have an observable, it gives you a real number. If the observable is continuous bounded, you want, in average, to converge to the average of what you see on the limit. And once you show convergence in distribution, there are many ways of showing convergence in distribution not using this definition. Well, for free, you get that if you show convergence in distribution in an abstract space, you can compose it by continuous functions which are real valued, which are, let's say, observables, and you can get concrete combinatorial information on your objects if you know continuous functions on your space. As soon as you have a continuous function on your space, you're happy. Are there any questions on this framework before I give a concrete example with a Brownian continuum random tree? Let me just do that. Great. To define the Brownian continuum random tree, I first need to define the contour function of a tree, of a plane tree. To do that, you have to take your favorite animal, you put it at the root of the tree, then you train your animal to climb in the tree at unit speed, and in a very well-behaved manner. So your animal will do the contour of the tree like that, and you look as time evolves its height. So my favorite animal is the capybara. So it climbs on the tree. You get the contour function of the tree. You look at the height as time goes. And then you get rid of your animals. No capybaras were really hurt during the fabrication of the talk. And this coding is very nice because if you know the contour function, you can get the tree very easily. You view it as a strip of paper, you put glue underneath, and you glue it like that. Okay? And using this notion of coding functions, we can state a result concerning the contour function of a uniform plane tree with n vertices. I'll just show the following result. In the early 90s, you take the contour function of uniform plane tree with n vertices, you scale it in space and in time, and you have convergence in distribution in what space? The space of continuous functions defined on 0, 1, which are real valued, equipped with the uniform topology, very nice functional space. Why do we scale by 2n here? Well, because the tree has n vertices, thus n minus 1 edges. Every edge is taken twice by your animal, so 2n is roughly the time needed by your animal to do the contour of the tree. And square root n indicates that the typical distances in the tree are of order square root n. And what is the limit? The limit is the so-called Brownian excursion. Informally speaking, it's Brownian motion, the scaling limit of plus 1 minus 1 random walks, but under a excursion type conditioning because the contour function stays positive and then comes back to 0 at the end. So informally speaking, this is just Brownian motion conditioned to be back at 0 at time 1 and to be positive before that. Of course, it's an ill-defined conditioning. You have to be a bit careful how to define it, but it's perfectly possible. And an interesting consequence of this is that since the supremum of a function, of a continuous function on 0, 1, is a continuous functional, meaning that if you have a sequence of continuous functions on 0, 1 converging uniformly to some function, their supremum converges to the supremum of the limiting function. For free, you get a limit theorem for the height of the tree. Okay, because the height of the tree is just the supremum of its contour function. And what is the limit? Here, it's the tail of the supremum of the Brownian excursion, which is a very nice theta Jacobi function. And when this result was proved, it was a very important result because before this theorem, we knew that for many models of random trees, we had universality for the height. The height was of order square root n, and the limit of the tail, appropriately rescaled, involved this theta Jacobi function. So this we knew using analytic combinatorial tools. In the early 60s, using excursion theory, the fact that the tail of the supremum of the Brownian excursion was this theta Jacobi function was also known. And at that point, it wasn't clear whether it was a coincidence or not. How come the theta Jacobi function appears at the tail of the supremum of the Brownian excursion and in the height of random trees? And Aldous' result says that it's not a coincidence, and it's even, there's something even bigger happening. It's the whole excursion governs the geometry of the tree. And he showed this not only for uniform plane trees, but for more general bien-aimé Galton-Watson trees, which are critical and have finite variance. But in this case of uniform plane trees, the proof is very simple. You just use conditioned Donskoy's invariance principle, because the contour function of a uniform plane tree is essentially a conditioned random walk, which is not the case for general bien-aimé Galton-Watson trees. And this is where the square root n comes from. It's essentially the square root n of the central limit theorem. So do you have any questions concerning this Aldous result for contour functions coding these trees? So at that point, we are happy. We have a limit theorem, but not for the tree, for the function coding the tree. So to be really, really happy, can we find a way to say that these discrete trees converge into some sense to a continuous tree? In other words, can we find maybe a more appropriate metric space into which the trees take values? And that's not an easy question. And actually, the idea is to view trees as compact metric spaces by equipping the finite set of vertices with the graph distance. And this gives you a finite metric space, which is compact. And the reason why it's nice to do that is that there is a very nice distance on compact metric spaces. So it will give you a space of compact metric spaces. In other words, you can define a distance on compact metric spaces, which tells you how far apart are two compact metric spaces. And how do we do that? Well, first, the idea is to say that if we have two subsets of the same metric space, it's not that difficult to say how far they are apart using the Hausdorff distance. Okay, the idea is to look at enlargements. You enlarge x, you enlarge y. You stop as soon as one is contained in the other and vice versa. And this defines you a way to measure how far apart are two subsets of a same metric space. And if you have two compact metric spaces, well, how can you define their distance? They are not living in the same metric space. The idea of Gromov was to embed them in the same metric space. So to define the Gromov-Hausdorff distance, you take the infimum, so it's a huge infimum, you take an infimum over all metric spaces, over all possible isometric embeddings of x and y in this common metric space, and you look at the infimum of the Hausdorff distance. So it's a huge infimum. Okay. And it turns out that it defines a distance on isometry classes of compact metric spaces. You cannot tell apart two isometric compact metric spaces. So if you identify compact metric spaces which are isomorphic, it defines a distance. And this metric space is even Polish, so very nice to do probability inside. And Gromov, I think it was in the 70s, something like that, used it for geometric group theoretical purposes. And it took maybe 30 years for people to realize that this framework is quite well suited for limit theorems in probability. In particular, it's essentially an immediate consequence of Aldous' result that if you take edges to be not of length 1, but sorry, here sigma is 2, sorry. So it's 1 over square root n, sigma is 2 here. 1 over square root n times Tn, you converge in distribution in the space of compact metric spaces equipped with the Gromov-Hausdorff distance. So you have a convergence in distribution for random variables, which are random compact metric spaces. And what is this limiting object called the Brownian continuum random tree? You just take a Brownian excursion, you view it as a strip of paper, you put glue underneath, and you do it like that. And you get something which looks like this. This is an approximation using a uniform plane tree with 20,000 vertices. Do you have any questions concerning this part on scaling limits? So in what follows, when we will speak about scaling limits, it will always be for this Gromov-Hausdorff distance. Now back to the model of random recursive trees with freezing. So there's something quite natural that we would like to do, is to introduce a size parameter. How can you introduce a size parameter if you want to have, for example, in your model, only trees with n vertices? Okay, because, for example, I said that the uniform plane tree model with n vertices, you could get it by sampling uniform excursion of plus or minus ones, but having a certain length. So the price to pay is to work in a triangular setting. So what does it mean? It means that instead of taking a sequence of plus ones and minus ones, you take a sequence of plus one and minus one, which depends on n. So as n grows, the sequence of plus one and minus one changes. Okay, this is exactly, for example, the case of uniform plane trees with n vertices. We want an excursion of plus one and minus one of length 2n minus 1. When n changes, well, the plus 1 minus 1 changes. So let's start with the subcritical regime. So this is a picture of the what happens for the subcritical regime. Okay, so now some notation. Here we are in a triangular setting where a sequence of plus 1 minus 1 depends on n, and we assume that up to time n we have active vertices. So this answers a bit your question. We assume that before time n our epidemic has not ceased, we have still active vertices. And you write Tn for this uniform random recursive tree with freezing, obtained by reading the sequence of plus 1 minus 1s given by xn up to time n. And informally, we assume that if we scale in time n space our evolution of the number of active vertices. Remember that Sn counts the number of active vertices, so here at time nt. So we assume that at time nt we have roughly n to the power alpha active vertices, and this is governed by some driving function f. If we are in the non-triangular setting, when the plus 1 minus 1 do not depend on n, this is just saying that sk is of order k to the alpha, and the function f of t is t to the alpha. So if you are outside the triangular setting, your function is imposed, but if you work in the triangular setting, you can have functions f which are very different. For example, in the uniform plane tree case, the function f will be Brownian excursion. So we have several assumptions which are a bit technical, but okay, I wanted to write a formal, a precise result. So really keep in mind this, informal statement. We need this function f to satisfy 1 divided by f integrable. We need a convergence of the inverse of the evolution of the scale number of active vertices to 1 over f in a L1 sense. And we need a second moment condition, convergence, in sort of L2 lock on every compact subset of 0, 1. I will discuss some of these assumptions a bit later. Maybe to explain just quickly, why does 1 over f appear? It's because since sk is the number of active vertices, if you have one vertex active and you want to know, does this particular vertex get affected at a certain step? Does it get freezed? Or does it get attached, or does there a vertex who is attached to it? Well, since there are sk active vertices, the probability that you choose this one to do something with it is 1 over sk. So this is why 1 over sk appears, essentially. And why does this square appear? It's essentially because if you take two vertices and you want to track how to go from one vertex to another, you have a square that appears, very informally. So this has something to do with the height of one vertex, and this is something to do with the distance between two vertices, very informally, just to explain the assumptions. Great. And so the result we get, which is joint work with Étienne Belin, Arthur Blanc-Renaudy, and Emmanuel Camerer, is that in the subcritical case, alpha between 0 and a half, Tn converges in distribution to a straight line with this length for the Gromov-Hausdorff topology. This means that of course, this thing is not a line. It can have outgrowths, but these outgrowths are little o of n to the power 1 minus alpha. Do you have any questions on this regime? Now, the critical regime so same assumptions. Here we have also an additional technical assumption, which is the evolution, the maximum number of active vertices you see is big O of square root n, which is the case for the uniform plane tree case, but it's a technical assumption. And here, we converge in distribution to some random, compact, real tree. So if you want, it's the segment you have seen before, but you take a lot of these segments, you glue a bit them at random, and you get a continuum random tree, which is compact. And there's something interesting going on, is that if 1 over f squared is not integrable near 0, for f equal the Brownian excursion, this is the case, the tree is binary. Okay, so it means that maybe does it look like a binary tree? Yeah, more or less. Maybe here this branch point is not binary, but saying that this tree is binary in the limit tells you that, okay, maybe you have vertices with degree greater than 2, but if you look at subtrees grafted on them, how many are of macroscopic size? We'll have only maximum 3 macroscopic trees grafted on every vertex. So in the microscopical level, the tree is not necessarily binary, but at the large scale limit, you have only a binary large sort of tree structure. You see what I mean? Makes sense? It's like uniform plane trees. The scaling limit of uniform plane trees is the Brownian tree, which is binary. Uniform plane trees are not necessarily binary, but it tells you that in every vertex of a uniform plane tree, you cannot have a lot of macroscopic subtrees grafted on this vertex. Great. And when near 0, 1 over f squared is finite, the root has infinite degree. You have a sort of condensation phenomenon going on at the root, but only at the root. At the other vertices are binary. So maybe you're wondering, what is this limiting tree? How do you define it? Well, actually, this tree has already been defined by Aldous in a completely different setting. I think it was in the early 2000s. And it's connected to a non-homogeneous analog of Keegan-Mann's coalescent, which was constructed by Aldous. So let me explain what it is. So the tree will be defined in a projective way. So you imagine n large. I will define the tree structure on n vertices, then you add another one, another one, another one, and so it gives you a sort of increasing sequence of trees, and this limiting tree is the projective limit of this thing. So consider n particles born at independent uniform random times. So for example, particle B2 is born at this time, particle B4 is born at this time, and so on. Okay. And now you imagine these particles, and you imagine that they coalesce as time evolves. And here you start at time 1, so it's a sort of reverse time. You start at time 1. Here at time 1 you have 0 particles. Here at this time you have 1 particle, nothing happens. When you are at this time you have 2 particles. You have 2 particles, 2 clusters, so they can merge. They will merge at a certain rate. Then you go here. Now you have maybe, if these two have not merged yet, at this point you have 3 clusters. So any 2 clusters will merge at a certain rate, and so on. So how do they merge? At time t, between t and t minus dt, each pair of clusters merges at a certain rate, and this rate depends on t. This is why it's a non-homogeneous time, non-homogeneous Kigman's coalescent. In Kigman's coalescent, the rate of coalescence does not depend on t. It's fixed. Here, it depends on your function f. So depending on your function f, you will force things to coalesce faster or not, depending on f. So for example, imagine that this thing happens. Here, the first coalescence happens at this time between these 2 things. Then you have, at this point, 2 clusters, one here, one here. You get something like that. You can encode this by a binary tree. Leaves are the particles. Branch points are the coalescence times. You put a certain distance between vertices, which also involves f. So I will not enter details. And then you take the limit as n goes to infinity, and it turns out that you get a random compact real tree. So yeah, I really just want to give you the idea. There are some subtleties here, which I'm not going into. So just keep in mind that once you have your function f, you have a lot of randomness involved to build this tree T of f, because you have the birth times, which are random. You have the coalescence times, which are random. So if I give you f, to build T of f, you need randomness. You get a random tree. Okay? So in particular, the Brownian CRT can be obtained as a limit in this way. Indeed, remember that in this case of an excursion plus 1 minus 1, we get a uniform plane tree, and we know that the scaling limit of this uniform plane tree is the Brownian CRT. As a consequence, T of E is T of E. So what does this mean? This T of E, this is a random compact real tree obtained from a Brownian excursion, viewing it as a strip of paper, putting glue on it and doing like that. And this T of E involves 2 levels of randomness. You take your Brownian excursion E, which is random. You apply the previous construction with F, this thing. So you add more randomness. You take uniform particles, which are born at certain times. You add coalescence rate, and so on. So you get the Brownian tree in law, like that. Meaning that if someone samples the Brownian tree like this and somebody else like this, you cannot tell in law the difference. It's a nice consequence of this. Do you have any questions on this? And maybe just in 2 words, the motivation of Aldous was a nice identity. I think maybe it's called Jolin's identity. If you take the Brownian tree and you look at the profile of the random tree, of the Brownian tree, the number of vertices at a given height. Okay, so this is called the profile or the local time of the Brownian excursion, or the profile of the Brownian CRT. And it turns out that the evolution of this profile is a time-changed Brownian excursion. So the Brownian excursion is you read the tree from left to right, but if you read it from bottom to top, there's also a Brownian excursion, a different one appearing. So this was his motivation to understand this property and to introduce this stuff. Okay, so maybe I go quickly on the supercritical regime. So here we I will not speak about this case. Now the boundary regime, which is alpha equal 1. And in this boundary regime, essentially, we assume that the evolution of the number of active vertices is constant times the time. So at time I, you have roughly constant times I active vertices. Here, you need to go away from 0 because, of course, for I equal 1, well, S1 is 1, 1 divided by 1. So if you put I at least 1, this will never happen. So you need to get a bit far away from the first times. And then what we show is that we have something which is a bit like this phenomenon, meaning that the distance between a typical point and the root will be c plus 1 divided by 2c log n. And indeed, for c equal 1, you get the log n of the random recursive tree. But the height, these long tentacles, it's a certain quantity, which is the implicit solution of some equation involving a rate function. And for c equal 1, you get E, as in the random recursive tree case. But when c is less than 1, for example, if you do plus 1, minus 1, plus 1, minus 1, the geometry will be a bit the same, but you have a constant appearing in all the limits. And this encompasses the case of random recursive trees. You take only plus 1s, so this is c equal 1. And it is in this case which appears in the evolution of the height, the study of the height of the infection tree. And this is ongoing work with Emmanuel Kammerer and Delphin Zenizergue. So what happens is that at the beginning of the evolution of the epidemic, we can apply this result. But at the end of the epidemic, what happens can influence this constant. And actually, there is a phase transition, but okay, I don't have at all time to discuss that. So in 5 seconds, let me explain the main idea, which is very simple. The idea is to use an alternative construction of the random recursive tree with freezing using time reversal. In the case of random recursive trees, this is well known. You start with n vertices, and in each step, you select 2 trees. You will get a forest. You select 2 trees uniformly at random, and you graft the first one on the second one, and you keep the root of the second one. So at each step, you choose one tree, another tree, and you grab the root of the first tree on the root of the second tree, okay? So you start with n trees made with 1 vertex. In the end, you get a tree, and it turns out that this is a random recursive tree. And this was first seen in computer science in connection with union-find data structures, and it was used later by probabilists to study random trees. And in the case of the growth of the random recursive trees with freezing, the main difference is that you do not only do coalescence, you can also do growth. So instead of always grafting one tree on the other, sometimes you will add new vertices. So how does it go? Start with this number of vertices, which is the number of active vertices you get at the end after n steps. And you build a sequence of rooted forests by doing the following. You read your steps from the last, and if you have -1, so this is freezing, you add a new vertex. Otherwise, you do the same thing as before. So imagine that you have this sequence. The sum of this is 1. So you do 1 plus 1, 2. You start with 2 active vertices. You read -1. So you add a new vertex labeled 5 because you add it at time 5. At time 4, you have a +1, so you choose 2 trees among these 3, and you graft the first one on the root of the second one. And you label the edge 4 because the +1 is at time 4. Here you choose one tree then another, and you graft like that. Here at time 2, we have -1, so we add a vertex labeled 2. Here we +1, okay? And it turns out that we get a tree with the same distribution as the random recursive tree with freezing. So you have a growth coalescence process going on. And as a consequence, if you track heights, this is very well adapted. Indeed, for every I, the property of this construction is that at every time you have Si trees. So it means that the probability that a given tree is chosen is 1 over the total number of trees, which is 1 over Si. So when xi is equal to 1, the probability that a tree containing a given active vertex is chosen and gets grafted to some other one is 1 over Si. And in this case, the height of this vertex gets plus 1 because it's grafted to something. So for free, you get that the height of an active vertex is equal in law to a sum of Bernoulli random variables only when you add an edge, and they are independent, and the parameters involve 1 over Si. This is why 1 over F and 1 over Si appeared. This was the L1 condition, and you can do it also for 2 points, and this gives you this square. And to finish, just to show you this growth coalescence in action, this is the subcritical case. The critical case, this is connected to the Aldous-Pitman fragmentation of the Brownian tree. So here, when a vertex appears, you give it a random color, and when 2 clusters merge, you keep the color of the biggest one. So here you have something non-degenerate. Now the supercritical case. So here you see that towards the end of the process, so this is here, you have not a lot of clusters already, okay? And now the supercritical, the boundary case, this is the random recursive tree case. Here you have already a lot of active vertices. Essentially, you do only plus 1, so at the end you have a lot of active vertices. Clusters merge, but okay, you have only small merging. This is this case. And everything coalesces at the end. So that's all. Thanks for your attention.